Hello students, welcome to AKGEC Digital Studio. I am Sundeep from IT department. I am going to explain the graph coloring program of dynamic programming using backtracking. What is graph coloring problem? Let's talk about it. Using backtracking means there is a graph given with some colors. You have some given graph, there is a graph given and some colors also given for coloring it, and we have to color each vertex. Listen carefully, we have to color each vertex with condition that no two adjacent vertices have the same color. Means we have to color the all vertices present in the graph, but taking care of no two adjacent vertices have the same color. Let's take this example. Here 5 vertices are given, vertex 1, number 1, 2, 3, 4 and 5. 5 vertices are given. In the given graph there are the 5 vertices. There are 3 colors given. In this type of problem we have given a graph with some colors also. Here the 5 vertices are given with 3 colors, and colors shown by small m. Small m here is 3. It means there are the number of colors are 3, which are red, green and blue, RGB. Then we have to color each vertex with the condition that no two adjacent vertices have the same color. Then how to color it? Let us start coloring from vertex 1. If we give the vertex 1 red color, then second vertex is vertex 2, and we have color R, G and B. 3 colors we have. As we have given red color to vertex 1, then we cannot give red color to vertex 2. If we give red color to vertex 2, then it violates the rule of graph coloring, and then we try to give color green, that is color number 2. If we mark the colors 1, 2, 3, and we have given red, that is color number 1 to vertex 1, then for coloring vertex 2 we cannot give the color first color, that is R, and we try to give G, and we check the condition no two adjacent colors, no two adjacent vertices have the same color. One is red, one is green, that is okay. Now we again check the next vertices. Next vertices is vertex 3. So vertex 3, then we try from the first. Can we given it to the red color? Yes, we can give the red color to vertex 3, because the adjacent vertices which has been colored just before is of green color. Then we can give red color to vertex 3. Now come to vertex 4. Can we give the red color to vertex 4? Because no, because we have given the red color to vertex 3 just now. Let's try again next color, vertex green color. So can we give the color green color to vertex 4? Yes, we can give the vertex green color to vertex 4, and check the vertex 3, which is the adjacent vertex with 4, which is red, and we are giving green color to vertex 4, which is okay. Now come to vertex 5 and last vertex of this graph, which have 2 adjacent vertices, vertex 1, vertex 4. Then we try to give the red color to vertex 5. if we give the red color to vertex 5, it have the adjacent vertex number 1 which also have the red color. That means we cannot give the red color to vertex 5. Then we try to give color number 2, that is green color, to vertex 5, and we found that we have green color vertex 4 which is adjacent to vertex 5. It means we cannot give green color also to vertex 5. Then we try the third color to vertex 5, which is blue color. If we give the color blue to vertex 5 and check the condition of the adjacent vertices is 1 and 4, which is red and green. I have written from blue color, blue pen, which is here given, and the condition of adjacent colors, adjacent vertices is satisfied now. Then what is the colors combination has been covered? Vertex 1 is colored with red color, vertex 2 is colored with green color, vertex 3 is colored with red color again, vertex 4 is colored with green color, and vertex 5 is colored with blue color. This is the one of the solution of coloring this graph. Next, can we color it in different approach, different way? Is there any another way to color this graph? If we start from 2, color number 2, and we give color 2 to first vertex, means if we try to give green color to vertex 1, then we check for the vertex 2, can we give the red, because we starting from the 1, 2, 3, color number 1 is red, color number 2 is green, color number 3 is blue. Then we try to give the red color, which is okay. We can give the red color to vertex 2, that is not violating the rule, and rule is no two adjacent vertices have the same color. Then we come to vertex number 3, and vertex number 3, can we give the red color to vertex number 3? Yes, we can give the red color to vertex number 3, but here is color red we have also given, but we cannot give the red color which violates the rule. Then we try the second color, that is green. Can we give the green color with respect to this red color? Yes, we can give. It means we can give the red and green color to vertex 3. Then we come to the vertex number 4. Can we give the red color to this? Because the last coloring vertex is vertex number 3. We can give the red color to this one. Now come to last vertex, vertex number 5. We try to color this again for the second way, second option, means can we give the red color to this vertex? No, we cannot give the red color to this vertex, because vertex 4 is already red color. Can we give the green color to this vertex? No, because we have green color at the vertex 1 which is adjacent to vertex 5. Can we give the color number 3, that is blue, to vertex number 5? Yes, we can give the color blue to vertex number 5, which do not violate the rule. Means vertex 4 having the color red and vertex 1 having the color green, and the adjacent vertex number 5, that is in between the 1 and 4, can have the color number 3, that is blue. This is the another solution of coloring this graph, means green, red, and blue. This is here vertex number 1 green, vertex number 2 red, vertex number 3 green, vertex number 4 red, vertex number 5 blue. That is the second way or the second option for coloring this graph. Next, then we are coming to the ways of coloring. Means in the last example we have shown that there are the two ways for coloring the given graph. Then how many ways can be possible to color a graph? There may be the different ways or options of coloring a graph. There may be many options. So this type of problem can be solved by using backtracking. Means backtracking is used for finding all possible solutions or ways for finding a solution for a given problem. If we want multiple solutions, go for the backtracking. Yes, here we want multiple solutions for coloring the given graph, then we go for the backtracking. Now the questions arises, if only two colors given for the above graph, that is this graph, if there was only two colors given, can it be then graph can be colored or not? Second question is, if four colors given for the above graph, then graph can be colored or not? These are the questions, these are the type of logical questions comes in the mind when we try to color the graph. Means if we have only two colors for the above graph, the graph cannot be colored with the given two colors only. And if four colors options are given, then we we had only three colors, then there were the two possible options we have shown there. So it means if more colors are given for the coloring that type of problem, it means it can be colored easily. Next, the type of problems on the basis of these two questions. The graph can be colored with the given colors or not. If there are the m colors given, then graph can be colored with the m number of colors or not. That is the one of the type of problem which comes under the m coloring decision problem. This is the type of problem in graph coloring, the m coloring decision problem, also called chromatic number or m color problem or chromatic number problem, we can say. This is the first type of problem. Second type of problem, how many minimum colors can be required for coloring the graph? So we have given a graph, then if you want to find the how many minimum colors required for the coloring that graph, it means it is m coloring optimization problem that comes under this category. And number 3, in how many different ways the graph can be colored with the given colors? If we have given a graph and some colors also given, then how many different ways to color that graph? This is problem number 3, type of problem number 3. Then we have 3 types of problems here. So we use state space tree for finding the all possible solutions, because we are here for finding the all possible options for coloring a graph with the given colors. So we use the state space tree for finding the all solutions for possibilities with no condition. For example, if no conditions are given, means vertex number 1, 2, 3, 4 vertices are given and 3 colors are given, red, green and blue. And if no condition is given, then we start from the root node, and for coming to node number 1, means if we come to root node to node number 1, means first vertex we have to color. And if we choose the red color for vertex 1 and come to the decision, means here we do not have any decision, here we have decision that is the color vertex 1 is colored with the red color. Next, if we color vertex 1 with the green color, then we come to the this decision node, and if we color vertex 1 with the blue color, then we come to the vertex number this vertex with decision of coloring the first vertex with blue color. Means we have 3 decisions, we have to take one of the 3 decision for coloring vertex number 1. Means either we have to color vertex 1 with red color or green color or blue color. Means this part is for taking the decision for vertex 1. Now come to this one. If we have colored vertex 1 with the red color, then what are the options we have for another vertices? Another vertices, we have another vertices options are for vertex number 2. Again we have option red, green, blue, because there is no condition. And if we choose the vertex number 2 as a red color, we come to this, vertex 2 as a green color, we vertex this, we vertex 2 is with blue color, we come to this. It means when we choose the red color for vertex 1 and after that we are choosing color for vertex 2 only, means this is the first decision we have taken, and after that we have to take either of one decision here. Similarly, if we choose the green color for vertex 1, then for vertex 2 we have 3 options again, and if we choose blue color for vertex 1, then we have again 3 options for vertex 3. Now here, then come to this part. Now here we have chosen red color for vertex 1, again red color for vertex 2, then for vertex 3 we have another fifth again 3 options. So similarly, for from each vertex we have 3 options for coloring the vertex number 3. Similarly, for vertex number 4, this is the graph with all possibilities, comes with the vertices with all possible colors. This is called state space tree with all possibilities. Then here the many solutions are there, red, 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 again red, 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 green and red, so many options are there. This is the total number of possibilities if there is no condition given for coloring the graph. It means total number of nodes, what will be the total number of nodes when no condition given? This means this is the root node where we do not have any decision. This is level 0 or level 0 means root, one node was there. For taking the decision for node number 1, we come to level number 1. This is the level number of 1. Then we have 3 more nodes for level number 1. After that, when we take the decision for level number node number vertex number 2, then we had 9 nodes. 9 nodes means 3 from each node, and we had 3 vertices. So we had 3 vertices from here, and for each vertices we had again 3 options. Then we come to the level number 2. Then we come to the level number 3. We had already this thing from here, and for all the possibilities we have again the 3 options. Again for level number 3 we had this thing for at level number 3. After that we had the 3 options for each node again. It means level number 3 we had 3 into 3 options, at level number 4, 3 into 3 into 3 into 3 options. And when we try to solve this, this comes 1, this comes 3, this comes 3 to power 2, this comes 3 power 3, and this comes 3 raised to power 4. And when we solve this, this comes with the 3 raised to power n, what is the maximum, plus 1 minus 3 to power 4 plus 1 minus 1 divided by 3 minus 1. That comes with the this thing 3 raised to the power 4 plus 1 minus 1 by 2. That comes with the 3 raised to power n plus 1, and 3 is the constant here. It means we can take C as a constant value in the place of 3. Then we can say the complexity of this type of problem when no condition is given. We have the complexity is C raised to power n plus 1, which is again exponential complexity. By tracking, the node can be reduced. In this problem, in this state space tree, if we try to kill the some path, then we use the backtracking. Then the node can be reduced with the help of bounding function, but running time will be the same as C raised to power n plus 1, which is there. We have found that. Then how we use the bounding function here? So take this example again, 1, 2, 3, 4. There are the 4 nodes are given, and the condition is the same. No two adjacent colors are having the same vertex, same color. No two adjacent vertices have the same color. Then we start from the root node and take the red color for vertex 1. Then we come to this vertex, and if we try to take red color for vertex 2, then it is impossible with the given condition. Then we kill that node for further exploration, means we don't have to move further in this path. Then we try for the green, means after red, green can be there, means this is valid node up to this particular path. After that we had again 3 red, green and blue, and after green, red is valid. After green, green is not valid, means it can be cancelled. After green, blue can be there, and after red, if we taken the red again for the node number 4, this is node number 1, node number 2, node number 3, node number 4, then 4 4 again clashing. So this node can be killed. And if we take the green, it means this we can take, means red, green, red and green. So this color options can be taken. After that, if we take the blue, means red, green, red, blue, this option can also be taken. Again we check for the blue color, the red, green, blue. After that red, it clashes with the node number 1, which is here. So we can say here also red, green, red. After that red cannot be taken. It is also killed by the bounding function. After that, if we taken the green color, yes, it can be taken. So just we can see red, green, blue and green. Yes, red, green, blue and blue, which cannot be taken. It means if we try to go from this path and find that if we found the path, right path, or node has been killed by bounding function, then we try to come the next node and explore the next path. And if we found the path here, then we come back to its parent node, then we try to find the next path. If we had 2 valid paths, again that we go to the parent node, then we try to find this path and this is invalid. Again we go to the parent node, then we try to find this path. It means we go to the some decision node where decision can be taken or not, then we go to the parent node and searching the all possibilities with the bounding function or the given condition. It means we are backtracking in the state space tree for all possible options. It means the node can be killed by the boundary at the boundary or by the bounding function uh, due to the same adjacent node. So once valid, then go for the next vertex, and we found that the valid path, valid combination. Then we also try to search the next, the check for the another color also. So after that, go back to the third vertex, which I have already cleared in the above, and check for the another option, color options. So for this graph, we have red, green, red, green. That is red, green, red, green. The one of the option. For fourth vertex means where we have taken the last decision for which vertex. That is the fourth vertex. Again, red, green, red, blue means red, green, red, and blue. This was the another option which has been taken last decision for the node number 4 means we have given this, and last option we have taken for the green and blue for node number 4. That is for fourth vertex we had the two options. Then we backtrack to the third option, third node, and where we checked there is any possibility. Yes, there was any possibility, means red, green, blue, and green. Red, green, blue, and green. This is the only one option was there when we choose the red color for first vertex, and decision at the fourth vertex we had the two options, and decision at the third vertex we had only first option. Again we go to the second vertex by backtracking, means second vertex at the backtracking. Then we go for the blue, red is killed because the same adjacent vertices, and green is valid, blue is valid. It means for decision at the second vertex we have two options again, means we have taken the red color for the vertex 1, or we have fixed the red color to the vertex 1. There are the 5 options for there. It means when we have taken the red color for the vertex 1 and search the all options with the bounding function or the condition given, we have finally 5 options for that. And similarly we can check when we give it to the green color, and the same type of tree will be there. Similarly we have when the blue color, similar type of functions, similar type of state space tree with the bounding functions where the invalid path will be killed and valid path will be the colored. Then how many paths we can have? We can have at most e raised to power n paths, or the finally. It means 3 raised to power n is the time complexity for this type of problems. So using bounding functions, some nodes getting killed and other are valids. The use of the graph coloring. What is the use of the graph coloring? Graph coloring can be used at the coloring the maps of any country, any region. If we want to color regions in a map, then we have some regions with their boundaries. Then we have region number this. If we try to draw this is the region number 1, and second region is there. This is the region number 4. Yes, this is the second region, this is the third region, this is the fourth region, and this is the fifth region. So we have there 5 regions where each boundaries are given here. So then we mark each region with the numbering, means this is the first region, this is the second region, this is the third region, this is the fourth region, this is the fifth region. and we ensure that the paper we ensure that no two adjacent regions have the same colors, by which we can distinguish them easily. So, for coloring this type of map for in printing press, the paper has to be passed in the printing press for every color and every region again and again. Then solution for avoiding this extra work, we can have the graph coloring problem. We got the minimum number of colors required for the coloring. Then we have already discussed, we can find out the minimum number of colors required for this type of problems. Minimum number of times it has to be passed for the printing press. If we try to color this as red, and second one this is red, because these are not adjacent, so that can be colored with the red color. Means if we have the minimum number of colorings, then if we choose the red color, then region number 1 and 4 can be colored by passing the paper in one way in the printing press. So then the numbering of the regions, we can convert it into the vertices. Region number 1 vertex 1, region number 2 vertex 2, region number 3 vertex 3, region number 4 vertex 4, region number 5 vertex 5. Then it becomes the graph from a map, and when it becomes the graph, the problem becomes the graph coloring, and we can easily color the map. And after that we can easily color the vertex, and we can directly convert it into the map, because vertex 1 if decided as red color, then we can give the region 1 as red color. It means the coloring of regions in a map can be easily solved by using the graph coloring problem. Thank you very much.